Okay, everybody, we're going to do notes for our Fischer esterification today to make isoamyl acetate. This name derives from the fact that an alcohol named isoamyl alcohol also known as 3-methyl-1-butanol, also known as isopentanol, is the alcohol. So one thing you learned today, amyl is an old name for pentyl. Some medicines still have amyl in their names, like amyl nitrate. It's a potent vasodilator. And you know now that that's really pentyl nitrate. And that's the alcohol. The acetate portion of the name comes from the fact that the acid right here is called acete. It's not acetate, that's an ion, or the carboxylate portion of an ester. That's what ATE means here. It's acetic acid. Also known as UPAC, 2-carbon unit, ETHAN. FN is 2 carbons. It's a carboxylic acid. Those two are going to react together in the presence of a catalyst. Today's catalyst is H2SO4, sulfuric acid. Catalyst. Sulfuric acid is the most commonly used catalyst on Earth in terms of industrial chemistry. We make more sulfuric acid than any other chemical for this purpose. Not just this reaction's purpose, but it's a very general and effective catalyst. And we're going to condense these two molecules together. So right away, one thing experiment 8 and 20 have in common. They were both condensation reactions, where you bring two molecules together and create a larger molecule. A larger molecule. That's the synthesis step of condensation. While at the same time you lose a small molecule, such as water. So here's your isoamyl acetate as promised. You could have called it isopentyl acetate. These are all acceptable names that all follow a pattern that you must know before next week. You can also call it 3-methyl-1-butyl acetate. And the E ran off the page. There it is. There's 3 more names. Replace acetate with ethanoate. Replace acetate with ethanoate. That's 3 more names. I don't know how clear that's showing up on the camera. Might be a pretty sketchy video. We'll see. Finger looks good. All right. So when we do the scale up section of the midterm, I'm going to give you the name of a new ester, and I expect you to be able to research from just the name of the ester what alcohol you needed to use to make the ester and what carboxylic acid. More on that when we do that section. We're going to do the mechanism now. Mechanism. Sulfuric acid is a catalyst that's used a couple times. Here's the sulfuric acid. Here's a lone pair on the carbonyl of the carboxylic acid. So of all the oxygens I have here, only use the lone pair on the carbonyl of the carboxylic acid. Do not use any other lone pair, and protonate that carbonyl using the strong acid catalyst. And this is step 1 of the mechanism. The overall reaction is an equilibrium. That states that every step in the mechanism must also be equilibrium. We now have a protonated carbonyl, and we know the name of such things to be an oxonium. What its role is an activated carbonyl. Activated just means more reactive than it was before. So we're going to take a nucleophile that normally doesn't like to react, and that's the alcohol. Alcohols are poor nucleophiles, so they don't attack carbonyls normally until they're activated carbonyls. So now you need the lone pair on the alcohol, and it's going to attack the carbonyl. And we all know, I hope, that if you're asked the question, what is weaker, a sigma or a pi bond, I hope you all know the answer is a pi bond. The electrons are not as close to the nuclei. So the pi breaks. So step 1 was to activate the carbonyl. I will write that down when we summarize. Step 2 is the attack of the alcohol on the activated carbonyl. We generate this intermediate here with a new bond to a carbon that has a methyl, and O with a bond to H that I'll draw in a second. And a plus charge here, a different oxonium. Oxonium number 2. And then step 3 is to neutralize that oxonium using the catalyst conjugate base that you generated in the first step. There's the conjugate base of your catalyst. It's going to neutralize the oxonium in step 3. And you are at this stage here. Yeah, just go with, make it look like this a lot. And O, methyl, OH. And we have a blue H here. And how do we finish that off to make it into the ester? That would be step 4. Looking carefully at these two species that are my index fingers are on, it looks like I need to reform a carbonyl. There's a carbonyl here that doesn't exist here. I need to remove the H off the oxygen that has the carbonyl at the end. And I need to remove OH. It needs to go away. Hey, HOH has to be removed. What do you call that? The step where you take a molecule and remove water from it. Don't call it condensation. This is only one part of the condensation. All 4 steps constitute the condensation. The last step is the removal of water from a molecule, which is called dehydration. And it's acid catalyzed. You should not be surprised. The acid serves to protonate the O right here so it can leave. The base, here's the acid-base pair here. The base serves to take away the proton from here. My apologies for crossing arrows. It crossed over the equilibrium arrow to get the H. Sigma became what? Sigma became pi. You're going to have 2 bonds there. OH minus is not legal in a mechanism where sulfuric acid is present. I hope that is obvious. You can't have OH minus hop off here. OH minus is a strong base. Strong bases and strong acids never coexist. Don't pretend they do. So when it leaves, it has to have an extra proton. And we all know that will be water. OH picks up proton, becomes water. Sulfuric acid is used here, and it's made here. All in this one step. It's a catalyst again. It was a catalyst before. It was used here and remade here. So it was a catalyst twice in this reaction. And that is the mechanism summarizing step 1, acid base. And its reason was to activate the carbonyl. Step 2, nucleophilic attack. By the alcohol. Step 3. Step 3, we neutralized an oxonium. It's acid base. Neutralize oxonium, comma, regenerate cat. cat being short for catalyst. And 4. Dehydration. Acid catalyzed. The combination 1, 2, 3, 4 equals, not dehydration, condensation, aka dehydration synthesis, which I've already voiced. I'm not a huge fan of saying it that way because it's got the order wrong. The dehydration was the end. Why put it first? It implies it happens first. I do like the words though. They're perfect words. They're backwards. I think it's just for one reason. They didn't like the sound of synthesis dehydration. They didn't like it. Just like my mother. Oh, I'll put this on a video. My mom will be proud. She thought David Todd sounded better than Todd David. So you have in front of you a teacher that goes by Todd because she wanted to call me Todd. Yet my first name is David. Ah, the explanation of DTW finally is upon us. Okay. That's a good end to a video segment right there. Most people think the D was for a doctor. It was not. Thanks, Mama.